Welcome back to the deep dive. Just think for a second about all the tech woven into your day. Like those smart suggestions in your search bar, or when your assistant plays just the right song, or even how your photos get magically sorted. That's AI, right? It's not sci-fi anymore. It's this invisible force behind so much of our digital life. But have you ever wondered what's actually powering all that? What's the brain behind the magic? Well, today we're doing a deep dive into something really fundamental. The Tensor Processing Unit. You might have heard it called a TPU. Yeah, many of us use AI constantly, probably without thinking about the really specialized hardware making it tick. It's definitely not your average computer chip. So our mission today is simple. Give you a shortcut. Cut through the jargon and get you genuinely clued in about TPUs and why they matter so much. Okay, let's unpack this then. We've heard the name TPU, but what is it really at its core? And maybe more importantly, why was it even necessary? Why do we need something new?
Right, that's the key question. And what's fascinating is that a TPU is an application-specific integrated circuit, an ASIC.
ASIC. Okay.
Yeah, so it's not a general-purpose chip trying to do everything okay. Google designed it with a laser focus.
Yeah.
Its job is to be an AI accelerator, specifically for neural network machine learning. Think of it like, instead of a Swiss Army knife, it's a custom-built racing engine. Pure performance for one job.
A racing engine for AI.
Yeah.
I like that. But why couldn't the chips we already had do the job, like CPUs or even GPUs?
Great question. So traditional CPUs, your main computer processor, they're workhorses, right? Good at lots of different things.
Right.
But they're just not built for the kind of repetitive, really heavy matrix math that AI, especially deep learning, relies on.
Okay.
And even GPUs, graphics cards, which are much better at parallel stuff and got adapted for AI, well, they eventually hit a wall too, especially with the sheer scale and the unique precision needs of modern AI.
So both had limits when it came to these massive AI tasks.
Exactly. And that's where TPUs come in. They really shine because they're specialized. They significantly outperform CPUs and GPUs for these specific AI jobs. And it's not just a little bit better. It's a huge difference because they're built to handle a high volume of low-precision computation very, very efficiently.
Low precision. That sounds less good. Why is that an advantage?
Good point. It sounds counterintuitive, right? But for many AI tasks, especially inference-making predictions, you actually don't need super high mathematical precision all the time. By optimizing for lower precision, TPUs can do way more calculations faster and, crucially, using less power. That's the trick. It makes massive AI economically feasible.
Ah, okay. Less precision, but much, much faster and cheaper for the right kind of job.
Precisely. And this links to the next big advantage, superior energy efficiency. They get more input-output operations per joule. Think about Google scale. Billions of searches, photos, translations. Managing the power consumption is absolutely vital. TPUs allow them to do that without, needing their own power plant.
So it's like Google saw this huge AI calculation bottleneck and said, okay, forget adapting general tools. We'll build the perfect tool from scratch. That specialization must have been a massive boost for them.
Oh, absolutely. It let them scale AI in a way that just wouldn't have been practical otherwise.
Right, that makes total sense.
Yeah.
Now, you mentioned their unique design. This is where I get really curious. How do they actually achieve that speed and efficiency? What's going on inside the chip?
Yeah, let's peek under the hood. The magic really comes down to that custom architecture. It's fundamentally different from a CPU or GPU. It has parts specifically designed for neural networks.
Okay, like what?
Well, the absolute heart of the TPU is the matrix multiplier unit, or MXU. Neural networks fundamentally are all about matrix operations, multiplying huge tables of numbers together. That's how they learn, how they process data, how they predict.
Right, linear algebra, basically.
Exactly, loads of it. The MXU is a beast designed just for that. It can perform literally thousands of multiplications and additions simultaneously in a single clock cycle.
Yeah.
It's like a massive parallel engine purely for matrix math.
Wow, thousands at once.
Yeah. Then you've got the unified buffer, or UB. Think of this as super fast on-chip memory. It's SRAM, which is much faster than the main system RAM. It acts like a large set of registers, holding the data right next to the MXU ready to go. This minimizes delays, keeps that hungry MXU fed constantly. Minimizing memory bottlenecks is crucial for speed.
So fast math engine and super fast local storage right beside it. Makes sense.
And there's one more key piece, the activation unit, or AU. This has hardwired activation functions.
Activation functions. Remind me.
There are functions that decide if a neuron in the network should fire or pass on information. They introduce nonlinearity, which is essential for the AI to learn complex patterns, not just straight lines. Having these common functions literally built into the hardware hardwired means they execute incredibly fast without the overhead you'd get running them as software instructions on a general processor.
So every major part is custom built and optimized just for pushing neural network calculations through as fast as possible.
That's the essence of it. The MXU for the core math, the B for rapid data access, the AU for specialized functions. It's this tight integration and specialization that gives TPUs their edge for AI.
It's pretty amazing to think about designing something so specifically. I imagine it's a huge challenge compared to just tweaking a general-purpose chip design.
Oh, it's a massive undertaking. You need deep expertise in everything from silicon design and architecture to the software compilers and frameworks that actually use the chip. It's complex.
But worth it for the performance gain at Google scale, I guess.
Absolutely. The payoff in performance, efficiency, and ultimately the ability to deploy more advanced AI makes that investment worthwhile. It drives this constant cycle of innovation.
And speaking of innovation, you mentioned this isn't a static thing. These TPUs have evolved, right? They're not still using the first ones they built.
Definitely not. AI moves incredibly fast, and the hardware has to keep up or even lead the way. We've seen several distinct generations of TPUs, each one pushing the envelope.
Okay, so walk us through that evolution. What were the big leaps?
Sure. So the first generation, TPU v1, came out around 2016. Its main job was inference.
Inference, meaning using an AI model that's already trained.
Exactly. Taking a trained model and getting predictions from it, like classifying an image, recognizing speech, that sort of thing. It used an 8-bit matrix engine, very efficient for just running those models quickly.
Okay, so focused on deployment.
Right. But then came the second generation, TPU v2. This was a really big deal. The key change was adding floating point calculations.
Floating point, like
Yeah.
more precise numbers.
Yes, higher precision math. And this was crucial because it meant TPU v2 could be used effectively for both training AI models, teaching them from scratch, and inference.
Oh. So they went from just using AI to building AI. That sounds huge.
And it was a total game changer. It really accelerated AI research and development, allowing Google to train much larger, more complex models internally.
Okay, what came after V2?
TPU v3, the third generation. This basically doubled the performance of v2, and significantly, they started deploying these in large clusters called pods. Imagine racks filled with these chips, all interconnected with high-speed links, working together as one massive distributed AI computer. It showed huge improvements in system-level design, not just the chip itself.
So scaling up the power by connecting lots of them together efficiently.
Precisely. Then came TPU v4, the fourth generation, another big performance jump, more than double v3 again. And a really interesting variant arrived here, the v4i. The I stands for inference. The cool thing about v4i is that it doesn't require liquid cooling.
No liquid cooling. Why is that significant?
It makes them way more versatile and easier to deploy. Liquid cooling is complex and expensive. Air-cooled chips like the v4i can potentially go into more places, maybe closer to users, not just massive specialized data centers.
Interesting. More accessible power.
Yeah. And the evolution continues. We've got the fifth generation, TPU v5e. The E here kind of stands for efficiency. It's optimized for better performance per dollar, especially for inference, making AI cheaper to run.
So focusing on cost effectiveness.
Right. And the latest one announced is Trillium, which is essentially TPU v6. This promises another big leap in raw power, but also, interestingly, it's designed with sustainability as a key goal.
Sustainability. How does that factor into chip design?
Well, it influences everything. The materials, the manufacturing, how efficiently it uses power per calculation, how much heat it generates. The goal is to maximize the AI capability while minimizing the environmental footprint, which is becoming incredibly important as AI scales up.
That jump from V1 inference only to V2 training and inference seems like the most fundamental shift. Was adding floating point the main thing, or did supporting training require other big architectural changes too?
It was definitely both. Floating point was essential for the precision needed during training, yes, but training also puts different demands on the chip, like needing much higher memory bandwidth to feed data, different communication patterns between chips and a pod. It really required rethinking how data flowed and how the chips collaborated. It turned TPUs from just prediction engines into full AI development platforms.
And the sustainability focus with Trillium beyond just using less power overall, are there specific engineering tricks they use, like turning off parts of the chip when not needed or
Exactly, things like that. Sophisticated power gating, optimizing data movement to reduce energy, maybe even using novel materials or manufacturing processes. It's about squeezing every last bit of computation out of every watt consumed. It ensures AI growth doesn't hit an energy wall.
It's just this relentless push, more power, more efficiency, broader capabilities, now even sustainability.
Mhm.
TPUs really seem central to Google's whole AI strategy.
They absolutely are. This continuous evolution is vital. AI models are getting bigger and more complex at an incredible rate, and the hardware has to stay ahead.
So for you listening, you might be thinking, okay, this is cool tech, but where do I actually bump into it? Are these chips in my phone or my laptop?
That's the common question. And generally, no, they aren't directly in your personal devices, at least not yet in the same form. But you interact with their results constantly, often without realizing it because they power so much within Google's services.
Okay, like what? Give us some examples.
Well, Google search is a huge one. When you write a query, the speed and the almost uncanny relevance of the results. TPUs are working behind the scenes, running the complex AI models like RankBrain initially and now others that understand your query and rank the billions of web
The
pages.
faster, smarter search results.
Okay. Yep. Think about Google Street View. Processing all those photos, stitching them together, identifying street signs, blurring faces that requires immense processing of images. TPUs handle a lot of that heavy
Right,
lifting.
the sheer volume of data there must be staggering.
It is. And Google Photos, all the smart features. Recognizing people and pets, grouping photos by events, searching your photos by content like beach or dog.
Yeah, that always feels a bit like magic.
That's AI running on TPUs, analyzing and organizing your library. And remember RankBrain, Google's early major AI for search. TPUs were key. And looking at the very latest stuff, like Gemini, Google's most advanced large AI model family. TPUs are the engine powering its training and deployment. They enable those cutting-edge capabilities.
So search, photos, Street View, they're biggest AI models. They're pretty much everywhere in the Google ecosystem, just hidden away in the data centers.
Exactly. They are the invisible hardware backbone for Google's massive AI operations, both training the models and then running them to serve you features. They're powering so much of the next wave of AI, making your digital interactions smoother, smarter, and more intuitive.
Wow. What a journey we've taken from figuring out what a TPU even is, this specialized ASIC, to peeking inside at the MXU and unified buffer, charting that rapid evolution from V1 to Trillium, and then realizing they're the hidden powerhouse behind so many Google services we use daily. It
Mhm.
really is incredible engineering.
It really is. And, thinking about all this specialization, it raises a broader question, maybe something for you to ponder after this. How might this trend of highly specialized hardware, like TPUs for AI, shape computing's future beyond AI?
Hmm.
Will we see more custom-built chips, more ASICs designed for other really complex specific problems, maybe in, say, scientific simulation or drug discovery or financial modeling?
Instead of relying just on general-purpose CPUs and maybe GPUs?
Exactly. And if that happens, what does it mean for the future of those general-purpose chips? Does computing become more fragmented with specialized processors for specialized tasks?
That's a fascinating thought. A future with lots of different kinds of brains for different kinds of thinking?
It definitely leaves you wondering about the incredible ingenuity behind making modern AI work and where this path of specialized engineering might lead us next. It's constantly evolving.